As ready as we'll ever be, I think. Yeah.
Hey, so welcome everybody. Welcome to the Simons Institute, and welcome to this workshop on Beyond Satisfiability. This will be held most Tuesdays throughout the semester. As part of the Satisfiability Theory, Practice and Beyond program. Thanks very much to all of the organizers, Jacob Nordstrom, Nikolai Bjorner, Adnan Darwich, Ambrose Gleixner, Kuldeep Meal, and Martina Seidel. A big thank you to them for putting everything together for this Tuesday workshop. And I'll hand over to Jacob to introduce the workshop.
Thank you, Peter. So it's a pleasure to introduce today's speaker, Kuldeep Meal. Before that, let's just talk quickly about practicalities. So we're learning to run these new workshops a little bit on the fly, as it were. I think that the intention is to do something like this. Most seminars, not all, but most seminars in this series will be like 1+1. So something like 45 to 50 minutes to an hour of a regular seminar talk, which is completely self-contained. And then we'll have a break. And then for those of us who feel that, wow, this was really interesting, we want to go in deep, open up the hood, look at some of the, even look at all the gory details, then there will be a second follow-up, more technical talk in depth. Not all weeks will have this format, and a little bit we'll have to learn as we go, but this is the intention. So I am chairing this today. I'll try to, I'm not exactly sure what the setting is, whether you can just speak out your question or whether you can ask in the chat or you can do both. And I think that I'll let the speaker clarify, each speaker how they want the questions to be asked. I will try to help keeping track of the chat and insert any questions if that is requested from the speaker. I don't know if there's anything else I should say. I don't think we'll spend time on long discussions of CVs. It's more like we'll do this in the I don't think we do that at the Simons workshops, right? We just let the speakers get on with it and speak. So I would say, without further ado, Kuldeep, it's a pleasure to have you opening this workshop. So the floor is yours.
Okay. Hello, everyone. So let's get started. I guess about questions, I'll try to follow up, try to look at my other window for questions on chat. But if Jakob, you can answer at any point if I'm missing. So with that, let's get started. I want to follow up on the talk that at the boot camp on counting and sampling. Today, I'm going to focus on model counting, and I'm going to discuss what ingredients have been crucial in improvement of model counters over past few years, both from theoretical and practical perspective. So let's get started. Before I get there, I really want to acknowledge all the collaborators over the years. A lot of work that I'll be presenting is certainly of work with my collaborators, and they have been leading some of the projects. And a special shout out to Mate Sus, who is the maintainer of ApproxMC, which I'm going to talk in a lot of detail. So I'm going to talk about counting. The problem is you are given a set of variables, x1 to xn. We have a formula over these variables. Let's say sol of f is the set of solutions of this formula. The problem of satisfiability, the set problem asks whether this set is empty or non-empty. In case of counting, we are interested in computing the cardinality of sol of f. We'll be looking at approximate variant of counting, where we'll be fine with a 1 plus epsilon approximation of sol of f. What do I mean by that? The count that should be written should be within 1 plus epsilon factor with confidence at least 1 minus delta. The counter the complexity and also the runtime performance will depend on epsilon and delta. As you can see, the smaller epsilon or the smaller delta you want, we are going to pay more cost. Let me give a quick example to make sure we are on the same page. So if the formula was x1 or x2, then the set of solutions of this formula are all the assignments to x1 and x2 except 0, 0. So we have 3 satisfying assignments, and the cardinality of sol of f is 3. So a counter should return an answer as 3. We'll be okay with some approximation to this answer. And this is the setting that we'll be looking at. Why do we care about counting? Well, turns out there are a lot of applications. I'm going to, towards the end, I'm going to touch upon one of the applications to show how encoding matters of network reliability. I'll be very happy to discuss applications in more detail in the second follow-up session here. As the program is on SET and the theory and practice of SET. So the algorithms that we design are designed with a viewpoint that is heavily influenced by SET revolution. What do I mean by that? There are 3 things that are very crucial. The first observation is we have a SET. We'll be looking at a SET oracle instead of the classical decision oracle. In particular, the oracles in our case can return unset, and the unset comes with the proof of unsatisfiability. And if the formula is satisfiable, then we get a satisfying assignment. More importantly, we actually don't have access to oracle. We have access to solvers. And one thing that matters about solvers in practice is that their performance depends on the formula that we are going to deal with. To drive home this point more, one of the things about solvers is that they have sense of memory. So if you had 2 formulas f and g, and if you could write g as f and h, then most of the current CDCL-based solvers will find solving such f and g easier in comparison where f and g were completely unrelated. Why so? Well, during the time when you are solving f, all the clauses that you learn can still be used, because if C is implied by F, then C is also implied by F and H. So these are the 3 observations that are I'm going to keep coming back and referring to them in defending the choice for design of some of the algorithmic building blocks. In particular, I want to drive home this point even further. One of the building block that we'll be looking at are 2 kinds of calls. So thresh set wants to know whether a given formula has less than or equals to threshold many solutions. There may be another subroutine that we are going to be interested. I'm going to call it bounded set, where if the formula has less than threshold many solutions, then you should output the number of solutions of the formula. Otherwise, you output a symbol, say bot or no. If you were looking at classically from NP Oracle perspective, then thresh set can be implemented by 1 query to the Oracle, right? You write a formula that has, you make threshold many copies, and you say, well, are the assignments to each copy is distinct, and that can be done with 1 query. To implement bounded set, you will need to have threshold many queries, and the size of these queries can be f times threshold. So from the perspective of NP Oracle, these 2 subroutines will have different complexity. From the perspective of set Oracle, in case of thresh set, again, you can have 1 query, and the size of the query is f times thresh. For bounded set, since we can, at any point, our Oracle is going to return a solution, so we can make these queries where we get a solution, we block it, and we ask for the next solution, and so on. So in that case, the size of the query becomes f plus n times thresh, where n is the number of variables. Often it's going to be the case that n times thresh is very small compared to f times thresh. So in case of bounded set, we see that the size of the queries in the second case are what would be more favorable. In case of set solver, if I ask you how would you implement these two algorithms, well, you are going to say, find one solution, second, block it, ask for the second solution, then third solution, and so on. So from a set solver perspective, both the subroutines have the same complexity. This is going to be important because at some point I'm going to say, well, instead of thresh set, we can use bounded set, even though it looks like by asking for bounded set, we are asking more information in comparison to thresh set. So this is going to be, as you can see, when we are looking at from different perspective versus NP Oracle, set Oracle, and set solver, the complexity of different subroutines become different across these three viewpoints. Okay, so what am I going to talk about? I'm going to talk about, in case of approximate counting, there has been in last few years a lot of interest in hashing based techniques, and I'm going to discuss what makes these techniques work. I'm going to illustrate from three viewpoints: from algorithmic viewpoints, what has been crucial in the design of algorithms; from system viewpoint, because we are going to see that they rely on CNF XOR solving. I'm hoping at some point Mate Soos is going to give a possible talk in SET seminar to go in much more detail, and from conceptual viewpoint. So let's get started. Let me give a quick high-level overview of how these techniques work. So let the circle be the space of all possible assignments, and the dots represent satisfying assignments. So the key idea, kind of the overarching idea, is that if we could partition the space of solutions into cells that are roughly equal and small, then we can go and pick one of the cell randomly, and our estimate will be the total number of solutions in the cell multiplied by the total number of cells. To make these techniques work, one of the key things that we need to ensure is how do we partition into roughly equal small cells without knowing the distribution, and for that we rely on hash functions. So what are these hash functions? In particular, we rely on pairwise independent or two-wise independent hash functions. A two-wise independent hash function ensures that if you pick any two assignments and any two cells, and a function picked randomly from this family, then the probability H maps Y1 to alpha 1 is same as probability H maps Y2 to alpha 2, which is 1 over the total number of cells. We are picking over the assignment space, which is 0, 1 to the n, to cells that can be represented by m bits. So 0, 1 to the m is the space of cells. Furthermore, these events are pairwise independent. So the probability of H mapping Y1 to alpha 1 and H mapping Y2 to alpha 2 is product of the marginals. Why do we care about these pairwise independent hash functions? Well, the random variable that we'll keep coming to is the number of solutions in a randomly chosen cell. If we use pairwise independent hash function, then it ensures that the expected number of solutions in a randomly chosen cell is total number of solutions divided by total number of cells. Furthermore, variance is small. In particular, we can ensure that the variance is upper bounded by expectation. Once you have these two bounds, then we can use standard concentration bounds such as Chebyshev inequality, and we can say that our random variable of interest is bounded within 1 plus epsilon factor. And this expression here can be lower bounded as long as we can ensure that the expected number of solutions in a cell also has some sort of lower bound. Okay. So this is going to be kind of the entire recipe. If we use pairwise independent hash functions, then they can ensure that it's in expectation it is unbiased and the variance is small. And if we have chosen the value of m appropriately, then we'll be able to ensure that the number of solutions that in a randomly chosen cell is a good estimate of the total number of solutions of the formula. If there are any questions, I'll be happy to take as we go along. So one important thing is, where are these pairwise independent hash functions? So let me discuss the standard construction. So we have a set of variables, let's call x1 to xn. To construct a hash function randomly, what we do is we choose m random XORs. How do we choose each of these XORs? Well, we pick every variable with probability half and we XOR them together. So we might have something like x1, x3, x6, and so on. And the expected size of each XOR in this case is going to be n over 2, right? Because you are picking every variable with probability half. To choose a cell randomly, we can set these XORs to 0 or 1 randomly. So maybe we set the first one to 0, second one to 1, and so on. And now solutions in a cell is conjunction of the original formula and this m XOR constraint that we have derived. Okay. And at this point, we can invoke the set oracle, a set solver in practice, and count the number of solutions exactly if the number of solutions were small enough by enumerating. Remember, we just looked at the call bounded set, which is exactly that. Count me the number of solutions of a formula if they are small. So a set solver can just enumerate all the solutions. Okay, so that's kind of the overarching approach about hashing based techniques. Now I want to kind of, in this talk, I want to first focus on the algorithmic improvement that have been crucial. And of course, the hashing based approach goes way back to Stockmeyer's seminal work in 1983. It is a bit interesting that the approach I'm going to discuss is often attributed to Stockmeyer, although it was not fully listed in the paper, but the work of Jerome Vaillant-Vazirani credits Stockmeyer for the idea, and then Bellaire Petranque credits Jerome Vaillant-Vazirani, who is credited to Stockmeyer. So we are going to call it Stockmeyer's approach. So there are two observations that are important. The first is that constant factor approximation suffices. Why so? Well, let's say you had a method that gives a 4-factor approximation. Okay, so we have a method that gives a 4-factor approximation. So let me show you how you can use a 4-factor approximation to convert something into a 2-factor approximation. All we do is we construct another formula where we have replaced all the variables with another copy of variables, new fresh set of variables. And as you can look, that the number of solutions of G is square of the number of solutions of F. So if you had a method that can give a 4-factor approximation, then you can first invoke the method, get the 4-factor approximation, take the square root, and we'll be able to get a 2-factor approximation. Well, we can use this idea to convert any method that gives a 4-factor approximation to 1 plus epsilon factor by making 1 over epsilon copies, introducing fresh set of variables, and then we can take the 1 by epsilon root of the answer. Okay, so the first observation was that let's just try to focus on a constant factor approximation. How do we get a constant factor approximation? So suppose we had access to a method that could ensure that whenever the number of solutions of the formula is greater than 2 to the power k plus 1, let's say for some k, then it would return yes with high probability. And if the number of solutions is less than 2 to the power k, then it will return no with high probability. Suppose we had access to such a method, then I could get a two-factor approximation by just invoking this method for different values of k, and I can try to find the first time when this a comp returns no. So initially we are going to get yes, 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 and at some point we are going to get answer no. And the first point where it returns no is a good two-factor approximation, right? Just before that k, we know that the number of solutions is greater than 2 to the power k minus 1. And at this point, if it is returning no, then it is less than 2 to the power k. So it's a good two-factor approximation. For 1 plus epsilon factor, we can invoke this counter on 1 by epsilon copies, take the 1 over epsilon root, and return that as the answer. How do we implement a comp? Well, the idea is we can kind of the idea that makes it work is if we choose k minus 5 random XORs, then in expectation, we expect that the number of solutions is going to be 64. The number of solutions is going to be something of the order of 32. That the expected number of solutions is 2 to the power k over k minus 5. So it is 32. Then we can check, we can ask whether the number of solutions is greater than or equals to 48 or not. If it is greater than 64, if it is k plus 1, if the number of solutions is, sorry about that, if the number of solutions is in expectation 64, then with constant probability, we'll have the case that it's going to return yes. We can repeat this log n times, get the median, which is the majority answer, whether yes or no, and return that as the answer. We need to do log n times because we have to take the union bound here. So since we are doing a binary search, we are going to call log n calls to ensure that we get a constant factor. We'll need log n calls. And finally, we can return the median of these calls. And then just counter is going to invoke a comp log n times and then return the first k. So this is kind of the entire idea. And this was what was proposed long ago. So there are a few issues if you try to implement this. And if you try to look at that, what was stopping key bottlenecks that did not lead, that stopped this idea from realizing into very practical counters, there are two things. The first is too many calls due to union bounds. And the second is the queries are very large. Because if you look at work at set solvers, if you have to make multiple copies of the formula, then the solvers start struggling very fast. And even though in theory it is okay to have log n calls, but with in practice, you would want to avoid so many calls if possible. And due to union bounds, you end up having way too many calls. Once you put the constant corresponding to the Chernoff bound here, it becomes fairly, the scalability suffers a lot. So how can we try to fix this? Two things. The first is, instead of asking for a constant, such as 48, we are going to have this depend on epsilon. And I'm going to discuss how we can avoid making multiple copies of the formula. And then instead of trying to use union bounds, I'm going to discuss how we can introduce dependencies between different ACOMP calls so that we don't have to do these union bounds. So let me discuss the putting these two things together. What does the algorithm look like? Here is what it looks like. You start with the formula. You ask, is the number of solutions less than or equals to threshold? If the answer is no, we put an XOR constraint. We ask the question again. If the answer is no, we put 2 XOR constraints. We keep doing it until we reach a point where the number of solutions is indeed less than or equals to threshold. And at that point, our estimate is total number of solutions that we have found in the cell multiplied by total number of cells. Let me illustrate it more, and we can repeat the entire method log 1 by delta times and return the median. So let me discuss more formally what is going on here. So we start, the first query 0 was to ask, is the number of solutions of the formula less than or equals to threshold? After that, we put 1 XOR constraint and we ask, is the number of solutions of the formula and XOR less than or equals to threshold? And the query 2 is 2 XOR constraints and so on. And we want to stop at the first value of M, where the query M returns yes. And our estimate at that point is the number of solutions that we have for the query M. So remember the call that I talked about, bounded set, which would be able to return the number of solutions if it is less than or equals to threshold times the number of cells. So two quick observation here. Look at the formula that we construct for query I plus 1. What is that? Is the formula at query I conjuncted with an additional XOR constraint. So it is certainly the case that the number of solutions of at query I, the formula that we have for query I plus 1 is going to be less than the number of solutions for the formula at query I. So a quick observation is that if query I returns yes, then query I plus 1 must return yes. Well, we can use a logarithmic search because this relationship is deterministic. You don't need to amplify confidence at all. You know that you can use a logarithmic search. So the number of set calls we'll have to do with be log n. What is also nice is if we had to solve query I plus 1 after query I, we'll still be able to reuse all the learned clauses for query that we had for query I. From perspective about analysis, what one needs to ensure is if you look at the event EI, which is to ask what, so I'm going to denote EI as the bad event, which is to say that the number of solutions of the formula at query I is far from the, it should be this. The number of solutions of the formula at query I is far from the expectations, expected number of solutions. So these are the bad events. Then because of dependence, what you can show is that these events are contained inside others. So the event EI is contained in EI plus 1 for all the I less than M star minus 2. And also the events are contained inside each other the other way for all j greater than M star plus 1. Okay. So these two things combined together, I'm slightly being loose, so you need to set these bad events a little bit differently, but on a high level, that's what one can argue. So then we could show that the probability of error depends only on the 4 events. While we don't know what is M star, but the probability of error comes down to depend only on those 4 events. I'm going to come to this because this becomes crucial at a later stage. But one of the nice things about aspect of it is that we don't have to do amplification of log n, because there are only 4 things that you need to worry about. So no union bounds that we have to worry about here. Okay, so what does it translate to? Well, the algorithm that I just discussed gives an a 1 plus epsilon factor approximation with confidence at least 1 minus delta. Furthermore, the number of set calls we are making is log n. And one of the nice thing is that if the original formula is a DNF formula, then this algorithm gives rise to a FP-RAS, because all the bounded set queries that we were making, which is to ask is the number of solutions less than or equals to threshold, can be done in polynomial time. So we essentially get a polynomial time approximation scheme, which is of course randomized when the formula is in DNF. Okay, so now let me discuss how does all of this translate to practice. So we ran on these instances. I don't have the cactus plot for approximately 1, which was in 2013, but we know that in case of approximately 2, it can solve about 450 instances, and it on almost all the instances, it was about 10 to 100 times faster than approximately 1 that did not use this dependence and had to rely on union bounds and so on. So this was kind of the first important step that came mainly from looking from the algorithmic viewpoint. Okay. Now I want to discuss one more important aspect from algorithmic viewpoint, which is that the solvers, their performance depends on the size of XORs. So one of the things that we are interested in is, can we have shorter XORs? So one thing is, it would be nice if we could pick every variable with probability less than half, because we know that if we pick every variable with probability half, then the expected size of each XOR is n over 2. If we are picking with probability p, then it would becomes n times p. And if p can be very small, then we could ensure that the expected size of each XOR is going to be small. So what happens in that case is that you could show that in expectation, the number of solutions is still fine in the sense that this is unbiased, but the variance has this another pesky factor, which depends on the pair of solutions. W is the Hamming distance between these pair of solutions. And this is what this factor looks like. In the sense that this is a monotonically decreasing factor with respect to W. So what it means is that if there are a lot of solutions at small distance to each other, then the variance can shoot up very high. Of course, one thing you can observe here is that if P was half, then the entire thing just goes to 0. And we do have the case that variance is less than expectation. So the size of XORs really affect the performance of the solver. So this was identified as a key challenge very early on when the work started on hashing-based techniques and the practical implementation of these techniques. And one of the way you could try to upper bound this expression is to say that, okay, what I can try to do is that there are these two summations. So let's look at the summation inside. And I can try to write it to say that, let me look at how many solutions can be at distance W from a given solution sigma 1. In a Hamming space, we know that the number of solutions at distance W can be n choose W times, again, the same factor. But the problem was that n choose W grows very fast with n. So it becomes very hard to upper bound sigma square over expectation. And if you try to use These loose bounds, they will actually lead to slowdown, because now you have to deal with a large factor in your threshold computation, and that leads to slowdown. So recently, one of the things that we could do is just a simple rewriting of this expression that allows us to use very powerful isoparametric inequalities. So what do I mean by that? So let's look at this additional factor again. And now I'm going to say that let's call CF of W as the pair of solutions that are at distance W from each other. Okay, so what we are doing here is to sum over all the pair of solutions at distance W from each other, multiply them with the term R of Wn, because remember, this term only depends on the distance between the solutions. So then we could use, based on Rastian and Reynolds result, to show that this entire expression can be upper bounded by this term, AT square root NL choose W. What I want you to look at is that earlier this term would be N choose W, where L is the log of the number of solutions, which is often very small. So you get an exponential improvement. So what all of this translates to is to say that, well, you could upper bound variance over expectation by a constant if you could guarantee that the number of solutions of the formula are upper bounded by some constant times 2 to the m when you are putting m XORs. And that would lead us to improve the p from linear to logarithmic in terms of m. However, one issue that would come about when you try to use this result is to say that, well, there are no meaningful bounds on the number of solutions, because the number of solutions is exactly the quantity that we were looking to estimate. And this is where our usage of dependence comes in very handy, because all we had to look at are two bound probabilities of these 4 events. And one can look at it that whenever I had to bound probability of these 4 events, then I can bound these probabilities as long as I can ensure that when I'm adding the mth XOR, even though we don't know what m star is, but at every point, if I can ensure that I'm choosing the XORs with the probability in a way that the variance over expectation is bounded by some constant under the assumption that the number of solutions is upper bounded by threshold times 2 to the m. And we can realize this by making sure that we are picking mth XOR with probability Pm, which depends on log m by m. So this gives rise to an interesting kind of hash functions, because what happens is that I'm plotting here the PM on y-axis and m on x-axis. So we pick the first XOR with probability. In the first XOR, every variable is picked with probability 0.5. In the second XOR and so on, every variable starts getting picked with a smaller and smaller probability. So you initially start with very dense XORs, but as you go along, when you are adding more and more XORs, they become sparser and sparser. So finally, we get, I'm showing the plot where the variance over expectation is upper bounded by 1.1. This is just some constant that I put in. So as you can see that the higher the number of XORs we are picking in, the sparser they become. Okay. So how does all of this translate to practice? So here is some results to showcase. So if we include in approximcy, we add the sparse XOR, then here's what happens. A little bit of a surprise. It can lead to slow down, but then we see the cases where it leads to speed up. And the reason this is happening is it's very strongly correlated with the log of the count, because that's the number that determines the number of XORs we are putting, right? Remember, the answer we return is the number of solutions in the cell, which is less than threshold, times 2 to the m. where m is the number of XORs we have put in. So as you can see that when you are putting large number of XORs, then the XORs have become sparser. So that leads to the runtime of the underlying solver is much better. So we gain speed up, but that's not the case when the number of XOR that we have to put is very small. Then in that case, because for the new hash function we propose, we could bound variance over expectation by 1.1. As I mentioned, there is some constant. So that leads to an increase of 1.1 in case of threshold. And this is where the theory and practice comes in. You are increasing the threshold by 10%, and that actually leads to slowdown. So this pays off when the XORs become much more sparse. So even though you have to enumerate 10% more solutions, it turns out to be much better in practice because now the XORs are much more sparse. Okay, so that concludes the algorithmic viewpoint of the improvements that have been crucial in the performance of these techniques. So there are two things that I want you to take out from here. One is usage of dependence, and then which allows us not to have to work with very multiple copies of the formula. And also it allows us to use these sparse XORs. And in these two cases, we can get speed up compared to the what would have been the best implementation. Now, the second part of the talk that I'm going to discuss is focusing on the system part of it, which is that this formula that you have to solve are CNF XOR formulas. So how do we solve these formulas efficiently? If there are any questions, I can stop here for some time.
So one question is that there has been work on trying to get the guarantees from these completely random XORs by cleverly using error correcting codes. And
yes,
even papers publishing, claiming that this works. So it would be interesting to hear your view on what of this works and what maybe doesn't work and why or why not.
Yeah, so so it works in theory because you could get a fairly loose upper bounds on variance over expectation, but those loose upper bounds on variance over expectation would, as I mentioned briefly, is that the expression for threshold is this variance over expectation comes in the expression here. So in that case, the threshold becomes very large. So in practice, those methods, if you implement them, then they actually lead to slowdown, because typically you can bound this by very large. So the expression that have been obtained depend on the value of n, but even usually you would get something like of 1,000 to 10,000 as this ratio. So now you are left enumerating hundreds of thousands of variables at every call. So if you remember, what we had to do is that we initially start with the formula and we ask, is the number of solutions less than threshold? So if you are enumerating tens of thousands of solutions at every step, it does not work in practice. If you try to use a set solver to enumerate 10,000 solutions, that's not going to work. So in practice, this leads to a slowdown. So this is where the gap between theory and practice is, that these bounds are very weak when all the work that has happened based on error correcting codes. So for some.
So, Kuldeep, I have another question. So, the isoperimetric inequalities that you mentioned, so how tight are they? I mean, is there room for squeezing them down further?
Yes. So I think these inequalities are tight for there exists formulas for which they are tight, but one of the thing that would be very interesting is if we could either do a test for whether these are the formula that we are dealing with, and then we can, because the worst case, they are tight for the worst case, but it's kind of fairly easy to test for that worst case. So the kind of solution space that has to be to achieve this bound, that's easy to test for. So for rest of the space, I think there's still a lot of space for improvement.
Hi, I had a question with respect to the sparse ZORs part. So there's this other line of work on sparse ZORs which deals with sort of getting to ISO like unique KSAT, reducing unique KSAT, and there are works by Kalbro and then by Trexler. I was wondering how the isoperimetric bounds compare to those bounds in those papers.
Yeah, so in those work, since the work that I'm aware of was focused on the ETH part, so there you required a lower bound on the number of solutions that are possible. So there it was fine to enumerate, to figure out, separate into the case where there are exponentially many solutions. So those bounds are good when the number of solutions is very large. While here, typically in case of most formulas, if you have a formula over 10,000 variables, then the number of solutions are very rarely in the range of 2 to the 900, but they will be much more in the range of 2 to the 100 or 2 to the 200, which is large number, but very small compared to the 2 to the n. So,
But I was just wondering, from an analysis perspective, do you know how the analysis compares? Because I'm assuming that analysis can still be done if you have few solutions.
No, the analysis there requires as far as I remember, it requires, it worked only in the regime of large number of solutions.
Okay.
So there's a question in the Q&A from Aditya Shrotri. Can you combine sparse hashing with row echelon hash to get even more sparsity? If possible, it may help for formulas with really large counts.
Yes, I think that would certainly help. We did not try it, but that would certainly help. Yeah, I think that would be interesting to try out. Okay, cool. So I guess I move to the second part. So the second part I want to focus on is the system part of it, which is that how do you have this, the formula that we have to deal with are CNF XOR, and they need to be solved efficiently. So there's possibly going to be a longer talk, but let me discuss some part of it.
So if we're going to have like within the next 15 minutes, say a short break, is that now or is it later?
I think after this, the second part. So the third
sounds
part.
Great. Perfect.
Yeah. So in case of what we had to do here is that this is kind of the standard. We had the CDCL algorithm, which works really well for CNF formulas, but it's not a very good algorithm if you have to deal with XORs. And for XORs, we know that Gauss-Jordan elimination is the efficient algorithm because these are just linear equations modulo 2. So the high-level architecture of how to deal with such formulas is to have the CDCL and theory. So the CDCL part is going to give the current assignment. The theory is going to check whether there are new propagations or new conflicts. If there are new propagations or conflicts, it returns back to the CDCL, and this goes on. And the theory solver should give a reason for propagations and conflicts. What is very important is you are always going to send these incremental updates, right? At every point, what happens is that the CDCL will make few more decisions. Then you give to the solver. It's like, okay, I have made few more decisions. Do you have something more to tell me? And similarly, what it's going to do, it has to, the theory solver should somehow remember the state from the last time and be able to do handle these delta updates efficiently. And the other thing that is important is that the reason, whenever there is a propagation, the reason does not need to be done eager, because the reason is used only during the config generation, so you may not even require it. So there needs to be a way of lazy generation of the reason when it is required. So let me discuss kind of our last 3 years. We have been working on making this CNF XOR solving efficient, and there have been kind of 4 components that we have focused on. The first is, it is advantageous if the entire formula can be in CNF form, because you typically want to use in-processing techniques in between, and for the soundness of all of them, it's much better if the entire formula is in CNF form. So one thing is that we can encode all the XORs into CNF. Let us do all the in-processing. And then we would need to extract all these XORs. And we would like to extract these XORs very efficiently. The second part that I just talked about is that we need some incremental update mechanism. We have been focusing on how to have efficient data structures and region generation. So let me try to highlight some of the work that has gone on to pique your interest. So one of the things is extracting the XORs out of it. So suppose you originally had an XOR which is L1, L2, L3 XOR together equals to 1. Then when we are blasting everything into CNF, these are the 4 CNF clauses that we'll have. But then maybe at some point among these 4 clauses, the first clause went through subsumption, right? So instead of L1 or L2 or L3, now you have L1 or L2. So it is still the case that these 4 clauses imply the XOR, but there's no equivalence. So in case of extracting the XORs, we are looking for all the XOR that are implied by the current set of CNF clauses. So that is something that we had to do. And the reason I'm emphasizing this is that the earlier work on detecting the equivalence usually goes through the pattern matching, which is something that you can't directly apply, because now you want to look for all these implications. So the number of patterns that you have to deal with grows very large. So this is where a lot of engineering that has gone on. The second aspect goes back to really beautiful work by Han and Jiang, which is how do you do this Gauss-Jordan elimination?
So you don't do pattern matching for the other thing?
We had to combine, so we don't do the exhaustive pattern matching. So what we had to combine is to look for the candidate clauses, which would be of this, which can be generated from the subsumption. So one of the things that we want to do is that we do it in 2 steps. First is to look for the candidate clauses by doing a Bloom filter match, because everything that is by the subsumption is a subset of the original set of clauses. And then we go over those, and we have to, at that point, we do slightly different sort of pattern matching.
So it is a variant of a variant, perhaps an easier pattern match or something.
Yeah.
Okay.
Okay, so now going back to how do we have this Gauss-Jordan elimination done? Well, the idea, just like the standard CNF XOR, so CNF solving, we do a 2 instead of 2 literal, we had to do a 2 variable watch scheme. Why so? Well, if you look at a XOR constraint, and if more than 2 variables are unset, then it cannot propagate or conflict. If there's only 1 variable unset, then it of course propagates. If there's nothing unset, then you either the clause is satisfied or is conflicting. But we have to also, not only we want to watch for propagation, but we also want to be able to do Gauss-Jordan elimination. So how do we combine the two? So to perform Gauss-Jordan elimination, if you recall, we need to always figure out that for every row, what's the pivot? So which is the column that can act like its pivot? So for every row, which is an XOR, we assign one of the variables as the pivot variables. And under the constraint that the variable that is pivot a variable can be pivot for at most 1 row, while the other variable is watching the XOR. So there are 2 variables that are watching. So one of the variable is assigned the pivot, and the condition is that a variable is pivot for at most 1 row. And what this allows us to do is, when we are doing the propagation, so as you see that when we are performing Gauss-Jordan elimination, the rows start getting combined. So the original constraint becomes, if you had an original constraint, now it's an XOR of sort of all the different constraints. But this scheme still has all the benefits that the 2 literal watch scheme has in case of CNF solving. In particular, when you are backtracking, if something was pivot for a row, then it is still a pivot. The watches does not need to be updated. One thing that can happen is that now the matrix looks different because the rows have been XOR. But that's okay, because these are just a combination of different rows. So even though you end up with a different looking matrix, but it's an equivalent matrix to the original set of XORs. So in this case, the things that have been very important in making all of this work is being able to extract XOR constraints, then keeping the CDCL and Gauss-Jordan elimination in sync for making sure that we have propagation. In case of conflict, we do this lazy region close generation, and putting these 2 things together. Let me show you. So I'll quickly. Looks like I'm missing. So I think once we come back from the break, I'm missing one of the plots, which is the performance improvement that we have seen over the years. So what we have seen is that from 450 problems that I just showed you, by putting these things together, we are able to, just let me go back to this. By putting these things together, we are now able to solve something of the form 1100 variables. So putting the XORs together, it gets us this efficient progress in case of systems, takes us from 450 variables to about 450 instances to about 1100 instances. So that is the progress that we can make by improving the underlying solver. So I think at this point, we are going to take a break. The final part of the talk that I wanted to go over was going to be over the conceptual improvements, which are the notion of independent support, and then encoding these problems in a different method, which is using projected counting. So this is what I plan to cover in the final 20 to 25 minutes of the talk, and then I'll take more questions and we can have longer discussion. Okay.
Okay, so now we have to decide on the fly how we do this. I guess in non-virtual seminars, when there's a technical second half, one has a break to be able to grab a cup of coffee or something, and that takes like 10 minutes. I don't know, do we want to do 10 minutes or a shorter break of like 5, or Kuldeep, any preference? Should we say 10?
We can do a 10-minute break, or I think I'll let.
Good. So then let's reconvene at 6:30 p.m. European time. I guess that's sorry, 6:40 European time, Central European time. I guess that would be 9:40 Pacific. Have a 10-minute break from now. Okay.
Hi, Kuldeep. Can you hear me?
Yes.
Would you mind? You are now assigned as host of this Zoom meeting.
Yeah.
Would you mind making me host?
Okay. Yeah.
Great. Thank you very much.
Yeah.
So it's 20 minutes to 7 European time, which was the time when we were supposed to reconvene. So Kuldeep, how are things on your side? I guess
Yeah,
it's like
I'm
what is
all
it?
ready.
Getting close to 2 a.m. or something like that.
Yes. I guess if you're a night owl, this is kind of a good time. So
Sounds fantastic.
yeah.
Okay, we're all ears. Whenever you're
All
ready.
right. So let me get to the sorry about missing this one plot that I wanted to show you. Well, if you're joining just after the break. So just before we went to the break, I explained the system part of improvements. And here is what we have been able to improve. So as you can see that it goes from 450 to about 1150, almost 1200 instances due to the underlying system improvements. And I think this is kind of very important to emphasize that to make these things techniques practical, one has to go beyond the traditional the CDCL solving on CNF formulas, because this formula that we have to deal with are turns out to be CNF XOR. And I think the same spirit is going to be important in other problems also as we go beyond satisfiability.
So Kuldeep, between
Yeah.
approx MC3 and approx MC4, I mean, I don't remember what's the new addition.
Yes. So in case of approximately 4, the two things that became fast was, one was that the reason clause generation, there was a lazy reason clause generation. And the other thing that became important is when how do you detect when a variable is set, then you have to suppose the variable that was the pivot variable and it gets set, then you have to look for the next pivot. And that computation was earlier happening in linear fashion, so that we could make fast by taking advantage of viewing the entire thing as vector and figuring out the first bit set. So those were the key improvements that made the performance difference.
Okay,
Sorry for
thanks.
being very under the hoods, but that's what made the difference. Does that answer your question, or?
Yeah, sort of. Okay.
Okay. Yeah. Okay, so now let me get into the third part, and I try to formulate a conceptual improvement. So this is where I think we can take advantage of the problem, and because the solvers are powerful, so we can let them do the other kind of queries that may not make much sense from pure theoretical viewpoint. but may pay off very well in terms of practice. So let me get there. So one of the thing is that the performance of the solvers really depends on the size of XORs. If the XORs are large, then the solvers struggle with those. So the question is, do we have to really put XORs on all the variables? The thing is, do we really require all the variables to specify the solution space of formula? Perhaps not. Let's look at the formula x3 if and only if x1 or x2. So at this case, you can
Can I
see
ask
that
one more question, Kuldeep? Yeah, in this
Yeah.
context. So, I mean, since it's true that large XORs make things difficult, but in the previous part of the presentation, you said that you're going to extract XORs. So,
Yeah.
I mean, do you sort of constrain yourself to extract only short XORs, or what if you end up extracting large XORs?
Yes, so I think that's a very good question. So what happens is that if you start with large XOR, then the way you encode these large XORs is that you will have to use this citin. You will have to cut these XORs to do the citin transformation, right? So the XORs that you encode in CNF are the direct translation of XOR is of size 4 or 5 or 6, around that. And then you combine these XORs to get a large XOR, right? So during citin translation, you are going to break these XORs into small XORs, and then you encode the entire thing into CNF. As you are extracting the XORs out, you will initially get small XORs, then you can combine them to get large XOR.
So you do end up extracting large XORs, but then that
Yes.
would be detrimental to the solver, right?
Yeah. Yeah.
That would be detrimental to the solver if you extract large XORs.
The thing is that, I mean, these are the XORs. So the variables that you are given are the citin variables, right? So either you can represent lot of rows or you can combine them together, right? Because if there are inherently large XORs present in the formula, then there's no way getting around them. You will have to deal with them. I can break a XOR into a lot of small XORs by introducing auxiliary variables, but that does not make the problem simple.
Okay.
Yeah. So going back, the observation that motivated us is, do you really require all the variables to specify the solution space of formula? Probably not. If you look at the formula x3 if and only if x1 or x2, then once I tell you the assignments to x1 and x2, it uniquely determines the assignment to rest of the variables, in this case x3. You can formalize this concept. You can say that a subset of variables I is independent support if for every two solutions of the formula, if two solutions agree on I, then they must be equal. So in this case, you can see that x1 and x2 is independent support, because once two solutions agree on x1 and x2, then they agree on rest of the variables x3. But of course, this does not mean that every subset of size 2 is independent support. For example, x1 and x3 is not, because if you assign x3 to 1 and x1 to 1, then x2 can take value 0 or 1. The important observation is that if we are given such an independent support, then we have to put random XORs only over the independent support. Is this going to help? Turns out yes, because as I just answered Supratik's question, when you are encoding, you end up introducing a lot of these auxiliary variables, and all of these variables are indeed dependent. So these encodings tend to introduce a lot of auxiliary variables, and it would be nice. One source of dependence that comes from is these encodings. Also, of course, in the underlying problem structure, you often have a lot of dependent variables. So the question is there an algorithmic procedure to determine the independent support? Of course, the idea about independent support is not new. It is certainly at least 100 years old. So let me relate it to the classical notion of definability. And the relationship is very straightforward. If I is independent support, then rest of the variables can be defined in terms of I. So I'm going to say the x minus I rest of the remaining variables are defined. A quick observation that is important in coming up with the algorithmic procedure is to say that if I is independent support and I can define xn in terms of I minus xn, then I minus xn is independent support, right? Because I can define rest of the variables in terms of I, and now I know that xn can be defined in terms of I minus xn, so I minus xn is the only set that matters. So we can, what this implies is that we can look for independent support iteratively. We can start with, we can check for one variable at a time whether it should be part of independent support or not. Okay. So this, of course, goes back to the classical classical Pado's theorem, which says that if xn is defined in terms of I, if and only if, again writing the definition, which says that if f of x and f of y, what it says is that if you take two copies of the formula and if two solutions agree on all the xi, xi equals to yi for all the variables in the independent support, then they must also agree on xn, right? A very crucial observation that becomes very important in practice, and I think I just want to highlight here, is that this would equivalently translate it to f of x and f of y and xi equals to yi and xn and not yn, or this same copy of the entire formula and not xn and yn. Now, making this observation that whenever this is unsatisfiable, then the second formula is just equivalent, where you just replace xn and yn. So if one of the formula is unsatisfiable, the other one is also going to be unsatisfiable. So instead of checking for the entire formula of all of these two, we can just check for one of the sub-formulas. And I think this is where the vagaries of set solvers come in place, because if you try to look for the entire formula, then the checks become very slow. But if you try to check for the unset of just one of the subformula, then it is very fast, because these will cause unit propagations immediately. So this is something that we learned it hard way. So only after we realize that you have to check for only one of the subformula, the check becomes fast, very fast. Okay, so what do we do? Well, we initially start with the entire, we set I equals to x, and then iteratively we remove a variable from the I. We check if it can be defined in terms of I minus xi. If it is, then we remove it. If it is not, we keep it in the independent support and we keep doing the checks. If you have n variables, you can perform O of n set calls, and you will finally end up with a independent support. What I find very interesting about the entire idea here is, remember our earlier algorithm makes log n calls to the set oracle, right? And now I'm telling a procedure which says that first you make linear number of calls to set, then get the information about the independent support and put XORs over this independent support. So this is where viewing things from the lens of set solver, things make sense, because these calls are actually very simple calls. Instead of the log n calls that we are making in terms of counting involve all these XORs and fairly complicated formula, these are kind of very simple calls. And most of them can be done very, very fast. So now I want to get to the final part about and about projection. So this is the part about when we are looking at the problems, it also matters how we can encode these problems. So what is projected counting? It says that if we have a formula f over x union y, then the projected counting formulation is to ask, can you count the number of solutions of the formula exists y f of xy, which is that, can you project the set of solutions only over x? So just to make sure we are on the same page. So if I have x equals to x1, y equals to y1, and the formula is x1 or y1, then the number of solutions, the set of solutions projected just on x1 is 0, 1. So there are two solutions to this formula if you project them on just on x1. So the question is, how can we compute projected count? One approach you could think about is, let's perform the quantifier elimination. We can eliminate y, express the entire formula in terms of x, and then use these techniques that I just discussed. But the other observation that makes things very interesting is that, well, we don't have to change much. We can have the same algorithm with just a simple minor change. And these two changes are very simple. Put XORs only over x. And remember, the other call we had to do was, is the number of solutions in the cell less than or equal to threshold? In this case, we are going to enumerate all the solutions only over x. Okay. How do we enumerate? Every time we get a solution, we put a blocking clause, and this blocking clause needs to be only over the assignments over x. Okay, so going back, whenever we had to do this call here, we could, instead of the projected threshold can be implemented just by taking the formula, get a solution, put a blocking clause, get the next solution, put a blocking clause over x, and so on. And why am I emphasizing on using projection? The reason I'm emphasizing is that using existential quantification can lead to very small formulas that you have to encode and use the underlying counters. Let me illustrate this by a problem that is fairly interesting, which is, given a graph, let's say you have some node source and some node terminal, and you want to compute what is the probability S and T are disconnected. And let us assume that every edge fails with probability half. You can take a graph and convert into another graph when such that this property holds true. So this is, of course, the problem of network unreliability. And let me now discuss how you can encode this into counting problem using existential operator. So what we want to do is that we want a configuration over this all the edges. So these are what we want to look at as a vector of 0, 1, right? So every configuration, and we are looking at representing the set of solutions, and the configuration that we are interested are where S and T are disconnected, and we would like to represent a formula so that its solutions are the configurations where S and T are disconnected. Once we have such a formula, then all we have to do is to count the number of all such configurations. And the configurations are going to represent our corresponding solutions. So how do we do it? For all the nodes, I introduce the propositional variables. For all the edges, I introduce these propositional variables. And now for every edge E, I can encode such a constraint which says that the interpretation of all these propositional variables for nodes is that I would like them to take value 1 if they are reachable from source S. And the edges take value 1 if they are intact. So what I want to say is that if PU is reachable and the edge is intact, then edge did not fail, then it implies that PV is reachable. Now my entire formula is taking the conjunction over all these edges and to say that PS is reachable and PT is not reachable. Okay. But what happens is that if you look at this encoding carefully, it turns out that while for every configuration of the edges where PS and PT are not reachable, the formula will be false, but the node variables need to be existentially quantified. So what we had to do here is that we are interested in counting the configuration only over edges. So we'll, and these node variables are need to be existentially quantified. So what we want to do perform counting is over this new formula phi, but with the quantification over all the node variables here. So this is where instead of trying to get another formula which would have one-to-one correspondence, you can use the existential operator. So this this is kind of concludes the three different improvements that I wanted to talk about. And let me summarize all of these again. So the first I talked about is the algorithmic improvement. The second jump was about the system. And the third jump was about this idea about using independent support. So where we are computing the underlying independent support and then use it in the approximation calls. And you can see that all the three play important role in making progress. So to just illustrate on one of the applications, so I'll go back to one of the applications about the network reliability. Here is something that we did. We took one of the graph, which represents power grid of one of the cities in the US. And we wanted to compare reliability for all the networks here. So what we do is that, and we compare with the state-of-art techniques that are implemented using graph decomposition. So I quickly want to just illustrate how much progress that has happened is that if you just use the standard tools based on graph decomposition, they time out for all the instances. So on x-axis, I have listed the terminals. So these are different nodes. We want to compare the probability of all of these different nodes not being reachable from the source, while approximC can compute these answers consistently within 150 seconds. So let me quickly conclude by trying to sketch out and things, and I guess this will be, hopefully we can discuss in more detail. So where do we go from here? I think in terms of algorithmic things that would be interesting to do is one is, can we construct sparse XORs? Something that Supratik alluded to in one of the questions is that how tight are these bounds? So these bounds are tight for some instances, but can we design sparse XOR that depend on the underlying formula that is given to us? One of the other observations that has been consistent in these hashing-based techniques is that the answers you get are really accurate. So it would be very nice if we could also prove that in practice, while the observation in practice is that the answers we get out of running these tools are very accurate, but the theoretical bounds are very conservative. So it would be nice if we can bridge the gap between theory and practice here. From system perspective, one of the things that we have not been able to utilize so far, focus on is how to utilize the fact that we can have sparse XORs. It would be interesting if we can improve either the proof generation, because one of the calls that has to happen is the unset call. So maybe take advantage of that. Another thing that I did not go into a lot of detail is there exists is exact counters, which are based on a very different philosophy on based on this kind of knowledge compilation. And it turns out they are very complementary. There are problems where exact counters would work much better than the approximate counters and vice versa. So it would be nice to look into having counters that are of hybrid nature. Finally, from conceptual viewpoint, I think two things I would like to highlight. One is that the notion of independent support preserves the count exactly. But we are interested in developing techniques where we are looking at approximate counts. So what would be an equivalent notion that preserves approximation? And how would we compute those set of variables and the counts over those and so on. And then the last part that I think I would like to highlight is the thing that has been very crucial in set solvers performance improvements over the last few years is the whole notion about having a proof. When the solver returns a unset, it comes with a proof. What's the equivalent for approximate counters? We would ideally like to use an approximate counter for an instance where we don't know the exact count. So in that case, what is the proof that the answer we have written is correct? So with that, I would like to conclude. I'll be happy to take more questions, have longer discussion here. Thank you, everyone.
Thanks a lot, Kuldeep. I'll applaud on behalf of all listeners and some other claps. Let's open up the floor for questions. We've already had a few, but I think there's room for more. So one, while other people are thinking about their questions, like, could you elaborate what a proof of correctness would even mean in this context?
Yeah, so
for you,
I guess there are two things. One, of course, is that we have this CNF XOR formulas. So kind of very system level is having a proof format, and that would work for Gauss-Jordan elimination, something that Stefan and you have recently worked on. So that would be interesting to integrate. The other thing that is, how do we guarantee that we'll have to figure out what assumptions on randomness would be justified, which is that the queries we are constructing, especially in case of sparse XORs, where it turns out that in practice you can use even more sparsity than one can guarantee in theory. But of course, in that case, you don't have any guarantees about correctness. So we would need some sort of assumption about that these queries that you are generating are random, right? Because you have only done some queries. So either agree on the source of randomness, but I guess we'll have to ask how are we going to check it later on. So that's one question from which is more based on that this counter ran, and along with it produces some trace that can be certified independently but based on some certain assumptions, right? So one of them was that the XORs were generated randomly and so on. I think the other line that would be interesting is if I give you a count, then how can you try to verify that this is a correct count? You could invert the whole Valent-Vazirani or this underlying argument. You can say that if the count is C, then you should put log C number of XORs, and then you can try to check if the formula is satisfiable or not. But as it turns out that that's kind of exactly the calls inside the algorithm that were the hardest to do. So in that case, the proof verification does not seem any much easier than doing the count directly. So that's another part where it would be nice if I claim some count, then if we can try to verify it fast enough.
I have a question.
Yeah.
So something you actually said, you said that in practice you can use much more sparse hash functions. So have you tried it with the benchmarks for which you know the solution? Have you tried it with constant width XORs? Does it give the solution?
Constant width does not work. I mean, yeah, so when I say it does not work, some formulas it will give the correct answer, but some formulas it gives a very bad answer. But what you can do is, I think, yeah, maybe I'll show. you can push this curve down and then it's kind of still fine.
But you don't have guarantee in that case. That's the point. Yeah.
We are not able to show, yeah. And
Okay. And one thing I don't quite get, I mean, I can imagine why short XORs are better, but on the other hand, while the solver is trying to solve this, it's generating very wide XORs itself, right? So you could start with the small XORs, but very quickly they will become large. And so is that such a big gain then?
yeah, so I think that's why that's a very good point. And you can see that it starts paying off only when you have put very, very short XORs. Okay. So there are two parts to this answer. One is that in case of independent support, what has happened is that you are putting XORs only over a subset of variables. So in that case, even during solving, you are not going to generate XORs larger than the independent support, right? In case of just based on using the sparsity, it starts paying off when the original initial set of XORs are very, very sparse. At that point, the payoff is, there is payoff. But if it's only a little bit sparse, so you know what you are kind of alluding to is, if it's only, you know, instead of 0.5, if you have only done something like 0.25, then it does not pay off much.
Thank you.
Kuldeep,
the chat is generating quite a few questions. And I'm reading them out because I don't think all participants can see them, even if the speaker and the panelists can see them. So the first one is sorry, Supratik, for cutting you off. I'll let you in shortly.
no problem.
So Sambas is asking for pointers to papers or surveys on the topics in the talk.
So I guess I will upload the version of slides with, I promise to upload the version of slides with pointers.
Okay, sounds fantastic. Paul Beam is
we just
asking,
had a, maybe I can just plug in that the new version of handbook is out. So we have a chapter on approximate model counting that does have the references. And
is there any version of that chapter online somewhere, or do we have to wait until iOS Press delivers?
I guess no,
already ordered copy.
We did not put it online, but we should be able to put it today or this week. Okay. Yes, tonight I don't want to make promises. It's 2:30 here, so yeah.
I thought your evening shift was only starting, Kuldeep. You make me disappointed. So Paul Beam is asking about weighted versions of counting, because you only described the unweighted version of counting. How do things change with varying weights?
Yes, so that's a so for exact counting techniques, just to kind of try to answer question broadly, it turns out that weighted and unweighted both behave approximately almost the same way. Having weights do not change in case of exact counting. For approximate, it has a huge impact. So, and there are still a lot of challenges that one need to overcome. One line of work has been reducing weighted to unweighted. In that case, you end up introducing more variables and more clauses, and the new formula that you construct become much hard than the original formula. So what is happening here is that you start with the formula and the weight function, and the new form, when you do the reduction, then the new formula that we get becomes much harder compared to the original formula. So that is something that would be nice to try to address. There's another line of work which is reducing the weighted counting. So in case of unweighted counting, what we are doing here is we are reducing unweighted counting to these logarithmically many set call. So the kind of lifting the weighted to unweighted to weighted, the set call becomes the max set calls. And now we had to solve these formulas max set subject to the XOR constraints. turns out that we don't have very efficient mixed solvers that can handle Gaussian elimination. So that's kind of big limitation that is facing those attempts which try to lift to the optimization queries. So that would be something interesting to handle. There's also another line of work where you are trying to rely on the underlying weight distribution. So there, the complexity becomes dependent on the properties of the underlying weight distribution, something like the tilt of the distribution, which is how skewed the distribution is. So if the distribution is nice enough, then those algorithms can work well, but otherwise they tend to struggle quite a bit. So yeah, these are kind of 3 different line of work, and all of them are still at fairly early stages in terms of overcoming scalability barrier compared to unweighted.
Two more questions, just catching up with the chat. Let's see. So Massimo Laria asks, Kuldeep, where can I find the more detailed description of the watch literals plus pivot scheme for Gaussian elimination?
The code is on GitHub CryptoMiniSet. The paper is the paper that we had for CAV 2020.
Okay, so CAV 2020 paper by Kuldeep et al., and then use the source.
This builds on the old ideas about from Han and Jiang, their CAV 2012 paper. So if you are only looking for the Walsh literal scheme, then that's the old idea by Han and Jiang. If you are looking for what I was describing here, then the CAV 2020 paper would be.
And I haven't forgotten about Supratik, but before that, Ryan Williams, if I understand correctly, there could be multiple possible choices for the independent support set of variables. In principle, you just need a set of variables such that when they're all set, the remaining truth values are determined. Is there work on trying different ways of choosing an independent support?
Yes, so we did, that's a very good question. We did look at this in our work in 2015, and we did not do a very exhaustive study, but there are a few observations. One, it turns out that some independent supports are better than others. So one thing is that there can be a lot of minimal independent supports. So it does turn out that some minimal independent supports are better than others. Usually the smaller it is, the better it is for hashing based techniques. We don't fully know that how to characterize which one is better. Another thing that would be very nice, I have no idea, is suppose I give you different independent supports. We did not try out something like this, but maybe you put some XORs on one independent support and some other XORs on the other independent support, if that can be helpful.
So Supratik, thanks for your patience, please.
No problems, yeah. So Kuldeep, my question was that when we say that CNF plus XOR, the performance degrades with increasing sizes of XOR, is this considering solvers that combine, you know, Gauss-Jordan elimination along with normal CDCL style stuff, or is it only considering solvers? I mean, when we say that there are large XOR clauses and this causes slowdown of the solvers, do we mean that if we encode those large XOR clauses as CNF clauses and then just run a standard CNF solver, then the performance slows down? Or is it the case that even if you had a Gauss-Jordan elimination plus CDCL kind of solver, even then having large XOR clauses slows it down?
So yeah, the performance slows down even when you have the Gauss-Jordan elimination, because in some sense, which Albert had at some point pointed out, is that the proof is going to be, you are going to end up having very large clauses that are going to form part of the reason, and the conflicts, and when you are trying to prove the unset, it is going to be large proof. So that observation is true for even when you have Gauss-Jordan elimination. One thing I kind of want to again emphasize is that little bit sparsity doesn't seem to help. A lot of sparsity is important to improve the performance. So if you go from 0.5 to 0.25, then once you start XORing them together, then it's probably not going to help. I mean, we haven't done very exhaustive studies, but these are kind of quick things that we have tried. So if you go from 0.5 to 0.25, not much difference. But if you can go to very small XORs, then it starts paying off. To answer, another thing just to point out is, if you are going to blast everything into CNF and giving into a CDCL solver, they just do not work. Does not matter what size of XORs you have. So even for the tiniest of the problems, the CDCL by itself cannot handle XORs. So I just want to point out is that in case of just CDCL, XORs by themselves are very bad. Doesn't matter the size.
Okay, so this is with Gauss-Jordan. I mean, whatever you said was with Gauss-Jordan.
Yeah.
Right?
Yeah.
Okay.
So this sparsity helps. A lot of sparsity certainly helps when you have CNF, CDCL plus Gauss-Jordan elimination. Little bit of sparsity, I don't think helps us. And if you don't have Gauss-Jordan elimination, then XORs are just really bad.
Thanks. Yeah.
And let's see, a question from Jarkko Savela. Have you explored using symmetries of the formulas to speed up the model counting algorithms?
Yes, we have looked into symmetries. In case of, so symmetries tend to help little more the exact model counters than, in that case, we kind of know what to do with the symmetries. In case of approximate model counters, one thing we can do is, if you put this, if you have symmetries, so that once you put the symmetry breaking predicates, and I give you the count for the solutions after putting the symmetry breaking predicates, and if you can somehow map, if you know more about the problem structure, then sometimes it is possible for you to map back to the number of solutions with symmetries. So in such case, you can first put the symmetry breaking predicates, and then use approx.MC to get the count, and then use the function to invert back and get the count for the original formula. Such use cases can happen in case of software. So we had a paper last year combining this with Alloy, the tool. And then in case of Alloy at the high level, because the language sees the program written at a high level, so it's able to figure out the right symmetry breaking predicates, and that helps. The other line of work, but it's more in the context of exact model counters, is they are based on this idea about component caching. So if two components are symmetric to each other, then we know that their counts are also going to be same. So in that case, we use kind of the classical, the standard symmetry break based idea. You use break ID to use graph coloring to figure out if two components are symmetric to each other. And then if they are, then you can just reuse the count from one of the components when you are doing this component-based model counting. So there are two approaches to exploit symmetry. And I think it helps much more in case of exact model counting. In case of approximate, we have to still figure out what to do. So in case of exact, what helps very well is that in the residual formula, you can still somehow use symmetry to not do to save on computation, which is something that we are not able to figure out what to do in case of XORs. Did I answer?
I think so, but we should ask the person asking the question, I guess. Do we have any other questions for Kuldeep? Let's see, we might have, yes, your question was answered, Kuldeep.
Thank you.
Any final questions or comments before we call it a day? So I'm checking that I didn't miss anything. Yeah, so I guess we can. So actually, let me wrap up with a final question. Then. So since we, this would be if we were at the Simons, we would have had this talk and a bunch of other talks, and then we would all have mingled during lunch and dinner, and of course over dinner we would have started hacking away at research problems. So although this research semester is virtual, like related to this area that you talked about today, what potential is there at the Simons? Like what would you get people involved in if you want them to get involved in something? What should we do?
I think what would be interesting, I guess, immediate problem is, can we get very sparse XOR that depend on instance? So because we live in the world of efficient set solvers, so it is possible that you can do some set queries to find out some more properties about the instance. And then if we can use that to argue that you can use very sparse XORs, that would be very nice. So it doesn't have to be, so right now the bounds are derived which are instance agnostic, right? So it just says that, okay, here is the bound on the distance between, it is the isoparametric bound, which is just an upper bound on worst case instance. But in practice, we have access to a set solver, and you could make some queries to figure out what the formula looks like. And if you can utilize those properties and get better bounds for sparsity, I think that would be very nice. And just to kind of motivate why I'm arguing in that way is that if you look at independent support, right, we are making linear number of calls to the set solver in practice, and which is okay, because these linear number of calls are much more efficient, and they make the logarithmic number of calls that we have to make for counting more efficient. So I would like to push us to use the solver, find some properties about instance, and if we can do get better bonds on sparsity. And the other thing that would be nice is what can we do for CNF XOR solving when we have very sparse XORs? So that's the two things, kind of one from system perspective, one from the algorithmic or theoretical perspective, would be very interesting, and I think it would pay off also.
Okay, so thank you so much again. Thank you for a great opening talk in our workshop / seminar series. I think it's time to call it a day. And I'm quickly looking at the schedule. So for this will be announced in due course, of course. But next week we're having Daniela Kaufmann talking about how to use algebraic solvers for circuit verification, in particular multipliers. And the week after that, Romain Vallon and Daniel Lebeur promised to take us into a deep dive of pseudo-Boolean solving. That's all we have for today, folks. Thank you.
Thank you.